All right, good morning, everybody. It's nice to be here. First, I want to say I will not be talking about AI and semi-supervised learning. I told Vierekio and Razvan this many times, but it's still this on the schedule. So I thought I would continue with the fiction that it was going to be this. But in fact, I'm going to be talking about fine-tuning language models and RLHF. And I heard from one of the lab leads this morning that you've already had some experience with RLHF. So for those of you who are already experts, you can have a little nap. So just briefly, as Razvan said, I've been at DeepMind since 2016. I lead a team that works on a wide variety of language model related topics. So you can ask me questions about a lot of different things, and I probably at least know someone who knows the answer. But personally, I'm actually working on sign language modeling because, you know, language is a lot more than what we currently might think it is. Yeah, so that's a bit about me. So I'm going to start this talk off with a motivating example. And actually, before I do this, sorry, it's been a few years since I've been doing this regularly, but I like a bit of an interactive style, so I will be sort of asking awkward questions and standing here silently for a while, and also I encourage you to just like raise your hand and interrupt me. I want to get more to some like kind of conceptual ways of thinking about some of this stuff than just a bunch of detail on sort of the latest and greatest techniques, because all of the latest and greatest techniques will be changed in this area in 2 months from now, because that is the world we live in. Okay, but the concept of pre-training language models, I think, is pretty stable and important. So I took just yesterday a pre-trained language model that has not been fine-tuned at all, and I prompted it with the prefix, why is fine-tuning used for language models, and then the sort of new line character. And the continuation was then, for what reason did the United States reject the Treaty of Versailles? Which of these statements most accurately reflects? It's sort of just hallucinating sort of exam questions, I guess you might get somewhere, which is very different than if you go to ChatGPT or Gemini and you ask this question. In fact, then I took the very same model that had been through a fine-tuning, supervised fine-tuning phase, and I prompted it with the same thing. And I got this lovely answer. Fine-tuning is used for language models for the following reasons. One, and then it even adds markup, markdown language stuff, so you get some bold task-specific customization. Language models are often trained on general-purpose data. Anyway, you can see that we've taken this thing, this kind of, thing that understands like the distribution of all possible uses of language in all different contexts and just kind of picks one and samples from it to something that is actually kind of able to answer some questions. And don't worry, I didn't use the chatbot too often to help me make any of this lecture. This is my language model entirely. So today, this morning, what we're going to do is talk about a little bit more about why we fine-tune language models, then talk about the difference of fine-tuning language models for language classification, that is when language is the input, but something other than language is the output, just very briefly, and also generation. Talk about supervised fine-tuning, which is a very simple but incredibly effective technique. Talk about some questions. Chawler just got done talking about the scale of these things, and you maybe, if you can get away with it, don't want to have to deal with all of those parameters when you're fine-tuning, and then end with a discussion of reinforcement learning from human feedback. So why do we tune these things? So that example gives you some idea. And what I'm going to argue is, and what is argued and has been shown sort of empirically, and there are theoretical arguments for why this is the case. So you can think about, like, basically language models are trained on all of the language that people have used in all contexts for whatever reason everywhere. And we can view this as a kind of marginal distribution where we're marginalizing over contexts, over speakers, and all of this sort of stuff. So we have a great deal of understanding about how language is used, but we don't always have clues to what the right context is when that language is being used. And so we would like to be able to get kind of into the right part of that space to do things with language. A second aspect of this is we can think about language models as representing words. All they see is other words. But linguists have actually argued for decades, actually, that this is a really good and concise way of representing meaning. And so we're maybe on somewhat strong philosophical ground. And then the other thing that kind of causes language models to do really well is what these models are basically being trained to do. In fact, they're exactly being trained to do is maximize compressibility of a string of tokens. And the patterns that occur in a local context are actually, if you can learn to extract and generalize a pattern that you're seeing in data locally, you're going to do a great job at compression. So the models, as they get bigger and more capable, they're basically able to seize on patterns that they're seeing. They're not only applying sort of static existing knowledge, what they're able to do is identify and use those patterns. So there's a bunch of useful stuff in there. But when you just sort of prompt them as I did without any sort of refinement, they just kind of, you can't really control them. So basically, our first goal with fine-tuning language models is to encourage these useful abilities, either the general ones, so pattern extrapolation, linguistic reasoning, instruction following, or specific ones. So maybe we just want to take this general purpose language model and train it to do English to Serbian translation. And that it reflects a difference in maybe the goals. Are you more a general AI researcher? Are you somebody who's trying to build a particular product? These are both valid. These are both important. These are both things you can achieve with fine-tuning. A second reason is to ensure safety and human value-aligned behavior. So, as I said, there's this, marginal distribution. We're marginalizing overall context, overall speakers, including, we try and filter out people who have, who are doing bad things from this data, but even with care, we can include harmful claims and false propositions and things like this. And fine-tuning provides a mechanism for limiting the harmful use of language models. So we want to encourage safe and beneficial applications. So, these are big models. Those, building them have the responsibility to ensure that they're deployed to good ends. All right, so let's start getting into the meat of things. So I'm going to distinguish here, just for categorization purposes, two tasks. Classification, where X is language and output Y is some, generally a low-dimensional prediction. So this can be like a sentiment label, like, yeah, it's good or it's bad, the author likes it, or, it could be a problem like, classify this into one of 1,000 topics, or predict the reading difficulty for, for school kids, or give a grammaticality judgment, or something like that. And these were, kind of the first problems that language model fine-tuning was applied to. And more recently, we've gotten very interested in the generation problem where X is some language and the output Y is also some language. And these are things like translation or instruction following or conversational chit-chat, things like this. And the focus this morning is going to be on the generation problem, but I briefly want to say a bit about the classification problem because it actually represents a slight difference in sort of how we thought about these models. And if you are faced with a classification problem, because they're still really important, you probably want to actually you might want to consider some changes, not just use one of these big sort of generative style models. So one way of thinking about what language models are in general is, not just that they don't even have to just assign a probability to a string. I mean, that's very nice. Probabilities are well understood. They give you good mathematics. But they might just assign a score to strings of text that represent something like the likelihood. But, maybe one way of thinking about the difference is there are language models that are easy to sample from, and therefore good for generation. And then there are models that are just good at computing scores of strings, but it's very hard to sample from. So Challer's lecture covered autoregressive models, and they are brilliant for sampling. We start with the first token, we sample the next one, and then so on, and pretty much proceed that way. Now there are other ways to sample. There are energy-based models and diffusion models that do have sampling algorithms. There's just nothing as simple as an autoregressive model. Now, if we think about the classification problem, we don't actually need to sample. The language is given to us. We need to predict something else. And so you might start to see a limitation of this problem of only kind of looking backwards when you're sort of making decisions. And so this is actually a figure that I took from Challer's slides. And one can actually adapt this, where when we make a decision or score a word, we don't just look back. We also look forward, because in the applications we're considered with, we're getting all the text all at once. We don't have to generate anything in any order. We've got everything we need. And so this makes sampling, really hard. You have to do like interesting stuff. But it means that that pre-training phase where we're trying to fit that whole marginal distribution, those decisions might get a little bit easier. Sometimes the relevant bit of context becomes super easy if you can just look ahead a little bit. And so we have techniques for efficiently pre-training models that look like this, that look both forward and backward. They're different. They're not really always probabilistic models, but they're very powerful for classification. So in particular, that's because they don't just necessarily provide good scores. Internally, to make those decisions about the scores, they're building representations, very efficient, compact representations of the language. And that representation is great to be used for classification. So we're not going to have time to talk about the details in this lecture, but these bidirectional language models, for instance, BERT, this is probably the first widely successful large language model, and it was because it was able to solve these classification tasks better than anything that had come before. So I've been in the NLP field since 2005, and BERT was like, oh God, we're out of the job. We worked on these classification problems extensively for years, and this just was a game changer. Second thing to be aware of is, these big GPTs are fantastically powerful. But actually, for a fixed training or inference budget, at sort of any scale, bidirectional language models are still state-of-the-art for classification problems. So if you really have a classification problem you care about, you probably want to, at some point, at least explore the possibilities that these bidirectional models will give you. Now, that being said, the way we sort of explore the capabilities of models is usually these days via a series of things. We try prompts, we try some in-context learning, and we see sort of if we can do that, and then maybe we get some data and start doing some supervised fine-tuning. These models aren't particularly promptable. They are to a certain extent. People are working on this, so they're less popular. They work very well when you have, for whatever reason, a lot of supervised fine-tuning data. And there are often very good reasons why you have that data. But if you're in a sort of new domain where you're going to be creating this yourself, you may find yourself sort of sticking with the generative stuff. That gives you a little bit more flexibility. But that's all I wanted to say about sort of classification problems with large language models, since generation is kind of where the excitement is these days. Okay, supervised fine-tuning is also known as learning from demonstrations, and this term comes from the fact that we think about fine-tuning as a kind of reinforcement learning problem in the abstract. And one way of training an agent to act in the world is not just with this reward signal that you've learned about, but actually just having an expert do the thing. And then train using what's sometimes called behavioral cloning, training a policy to do that. So we can do the exact same thing. So basically, we just assume that we have reference input-output pairs, and our inputs are going to be prompts, and our Ys are going to be the continuation that we actually want the model to start producing. So, this can look something like this. Our X's could be, please translate good morning into Serbian. The output can be, I'm not going to try and pronounce the Serbian. What is 2 + 2? 4. What is Serbia's second largest city? Novi Sad. Write a poem about EEML. And I think sometimes it's appropriate for models to not agree to to do certain things. And so at this point, we have basically a new language model training corpus. And to a first approximation, we just run further iterations of that teacher-forcing language model training that you just heard about in the last lecture. So, I mean, and that really is effectively it. Now, there are a few important differences here. And I do want to highlight them because in practice, when you start doing this, you're going to want to make some changes. So the first is, when we're pre-training the model, it's trained to generate absolutely everything. And at output time, we may actually not want to train the model to generate things that looked like prompts. First of all, if you're in a competitive AI landscape, it might start leaking, things that we're prompting if you are training it to generate those prompts. So often what this means is, in that teacher forcing phase, right now we have losses on every token in the sequence. And what I'm saying here is we will just mask out the losses on X. Now the model will still see those and it'll be able to use them to make decisions about what to predict at Y, but we won't actually be generating those sorts of things. Now this is actually something you should explore. It can affect quality. Sometimes it helps, sometimes it hurts. It's pretty common, but it is definitely a question. The second is signal. So, at the end of fine-tuning, we often use a learning rate schedule that sort of decays over time. And at the end, you're taking very small gradient updates. And when we start fine-tuning, we kind of reset. And we're using much larger learning rates again, and we're often going multiple times through this data because we really want to emphasize this is the behavior we want to see. And so you actually often run the risk of overfitting on that fine-tuning data set, and so you have to keep track of that with a held-out fine-tuning set. But we're really trying to get a lot of control out of that set of data. The third difference is, as I alluded to with these massive models, you may not want to train all of them just for pure cost reasons. You might be in a situation where you have one massive model and you have 100 different tasks you'd like to run it on, and you have supervised data for all of them. It may actually be possible for you to train very small edits to that model, even if it's a massive model, and use them. But if you were having to retrain every single parameter, you would keep track of, these would be massive checkpoints. It would be just inconvenient to load them, to use them, even to store them would be potentially difficult at some scales. And then a final point is related to this fact that we want to extract a lot from this data. So when you switch the distribution that you're training your model on, I think neural networks, we don't quite understand the dynamics, but there's a bit of a use it or lose it sort of dynamic that seems to be at play here. So if the model just has to do well on this task, it might start throwing away really useful latent capabilities that it actually needs to solve the general task, but you're just telling it to do well on this particular set of supervised fine-tuning data. And so one way that we deal with this is we want to add a penalty that basically prevents the model from changing too much. And that means it won't maybe do quite as well on the supervised task. We usually sacrifice something. But it will actually generalize far better because, of course, the name of the game is generalization here. And one way of doing this is with measuring deviation between the starting distribution or starting parameters and the updated distribution as well. And that's obviously something that's a bit new from pre-training. So actually, I'll just introduce these things here. So there are kind of two common ones. The first one, much more common. This basically just says we're going to measure the difference between this, so I'm going to call p theta, the updated, fine-tuned distribution, and p theta naught to be the sort of time zero base model that we're starting with, the pre-trained language model after we've got done training it on the internet. And this basically, the KL divergence is a quantity, the positive quantity that tells you sort of how far away from the reference distribution P0 you've drifted. In fact, it's formalized in terms of some information theoretic context, and it's kind of very widely used. Or we can also do something like say, well, I want to make sure that the parameters that I'm using aren't too far away from P0 or from the theta 0, which are the initial parameters. And for both of these things, you're actually going to, in practice, have a scalar multiplier at the beginning that just says, how much do I care about sort of staying close versus being far away? You're going to have to, in general, tune this on some validation data. There's no kind of right answer. In general, if you have very, very large data sets, you might be able to get away with less large diverse data sets, you might be able to get away with less regularization, but there's no sort of general rule of thumb here. It's just something you need to search. So one other thing I just want to point out here is that in practice, these KL penalties are widely used, but the divergence must be approximated. So, this is the formula for the KL divergence. Here, it's just the difference of it's the expectation of the difference of these two log probabilities. Unfortunately, the space of samples from p theta is literally every string in the universe, so sigma star. So that's a really, really hard expectation. And so we have to replace that with, a Monte Carlo estimate usually. And, in practice, we often just use whatever sample we are working with from the training data as if it were our sample. This is not complete, it's a biased estimate. It's also incredibly high variance. It's terrible in all ways, but in practice it seems to work. But you can, those of you interested in like in inference algorithms, there's probably some interesting work to be done here. On the other hand, though, weight penalties require no approximation, but for some reason they're not used quite as widely. And there is an interesting, when you start using these KL penalties, you can make some Bayesian arguments, for instance, that you're kind of doing a Bayesian update to your language model, your pre-trained language model, rather than something else. And I suppose that, those of us who like Bayesian reasoning, it's a pretty story. I don't know if it really practically makes a difference. So at any rate, these things are just important as one of your tools when you're dealing with the fact that your model, when you've got a very small amount of data and you want to get the most value out of it. So one thing is to do, just recognize the fact that your model might be sort of too aggressively adapting itself, and there are techniques to deal with that. Okay, so the second kind of interesting point about fine-tuning is that we, maybe don't want to tune everything, either practically or potentially even for performance reasons. In addition to those KL penalties, maybe if we're fine-tuning a fewer number of parameters, we aren't going to be able to overfit quite as badly. That seems kind of appealing. Certainly if we're fine-tuning all of them, we definitely can be overfitting and at least need a KL penalty or something like that. The second problem with, but when you start saying, well, maybe we make decisions about this, you have to ask the question, what parameters should we be updating? And this is massive design space. There have been papers, written about like what parts of these models you should be training. People have proposed the top layers of transformers, thinking that's where kind of the decisions are actually being made about what to generate next. That seems like it's important to get right. There are even things like just training the bias parameters rather than these big matrices. There are things like just training the layer norm parameters, which have this kind of interesting behavior of being able to turn off certain kind of circuits inside of the transformers. So they're actually quite powerful for modulating their behaviors, just the attention weights, things like that. But an extremely common approach these days is what's called a low rank approximation, or a low rank adapter, so LoRa. But there's a whole family of these things, and I'm going to just quickly go over this third one because it's a useful technique that you should have seen. So Cheller mentioned at the end of his talk the fact that there are these structured matrices that you can approximate a big dense matrix in a whole bunch of different ways. This is what sort of applied mathematicians like spend their days working on. But a really classic way is for us to, I guess I don't have a pointer, is to just say that we're going to factorize a matrix W by saying it's the product which has a d by d shape by picking an R that's much smaller and dividing it into these two rectangular matrices that are d by R and R by d respectively, and then multiplying them together. R then is called the rank of the matrix, or R then gives the rank of the resulting matrix. And then what we're going to do is everywhere we have a matrix that we would like to adapt, we're going to freeze our W naught. That's our initial matrix. And we're going to add this like correction factor, which is going to be this delta matrix W, and we're going to just add together the sort of normal activation that flows through it, and the X that's transformed into H via this W naught, and we're going to have this extra W matrix. And we're going to initialize this so that the product is 0. So at the sort of, when we start the fine-tuning process, this delta is going to be doing nothing. And when we then do backpropagation, we're going to be able to compute gradients with respect to A and B, which are going to be much, much smaller than the gradients with respect to W. And so this is going to make the optimization process much larger. So one of the kind of key things to keep in mind is we use these dynamic or adaptive optimizers these days like Atom, and they keep track of some higher order moments of like kind of how quickly different parameters are changing rate. This requires memory. In fact, we have basically 3 copies of every parameter that we want to update. And so if we can reduce the number of parameters, we can use much, much less memory, which is super convenient. And so at any rate, basically though, what we're learning is also conveniently though, just a like update to that W naught matrix. So if at the end we want to actually compile this down to a single checkpoint that is loaded, where we've actually updated the model, we can also do that. We can also do that here, where we just say, W0 is then we add the product AB to it and get this new updated matrix W tilde because of the. Because these are all just simple linear. This is just simple linear algebra. Yeah.
Do you actually change W naught or just AB?
Oh, you just change AB. Yes, sorry. To be clear, during learning, W naught is frozen and AB are updated, and yeah, that's everything. Okay. So one of the other things that the LoRa paper, which is one of the sort of good papers of the last few years for sure, did was look at, well, what actually should we be updating when we're when we're doing supervised fine-tuning. And they, for both conceptual reasons and then sort of empirically showed that it worked, argued that we should be updating, we should be controlling how attention works, because that's going to limit or guide the right information to be suppressed or to get where it belongs. And so, you know, one of the things they found, for instance, is that large rank matrices of, you know, kind of any of the single like matrices that modulate the behavior of attention don't have a huge benefit. But as you sort of co-adapt several of them, even with smaller rank updates, you end up with some nice increases in performance. And they looked at this across either holding the number of updatable parameters constant, where as they updated more matrices, they shrunk the rank, and also just looking at different ranks on different things. And basically, if you take these things two together, I think the real lesson that you find is if you update the queries and the values with a relatively small r, things work well. So the query key, this WQ matrix, keep in mind, what this is doing is it's saying at each time, what things do I want to be going out and looking for in the context of the transformer in order to make sure I've got the information I need. The value is saying, what information should I be propagating forward at this time step? And so by modulating those things, we get a lot of control over the behavior of these models.
Sorry.
Yep.
I have a question. Is LoRa applied per head or across the heads?
It is applied per head in the multi-head thing. So yeah. Yeah. All right. Okay, so here's a little pop quiz. So, one of the remarkable results is that LoRa isn't just fast, it's also better in a lot of cases. So here's just like a random demonstration of this where they compared it to full fine-tuning and actually a bunch of other stuff, and it's just like really good across the board. So what's an argument you might make for for why LoRa works better than updating everything? Yeah.
It's really hard to find the best type of parameters to fully fine-tune these large models, and they're on, and most of the time, maybe under-trained, so that you don't know where to stop and you don't have the budget to do all these hyperparameter searches.
Yep. It's hard to know. So his answer was, maybe we could have tuned these larger models, but we can't afford it because doing a big grid search to set the right hyperparameters, learning rates, and batch sizes, and all of this stuff is just too expensive at a large scale. I think that's absolutely part of it. Anyone have other solutions? Yeah. So that answer was divergence. So the mean squared error of the parameters or the parameter divergence, other sort of maybe policy divergences are also constrained. The model just has less flexibility to kind of overfit, you might say. So I think that's those are the two that I kind of came up with. So well done, you've both thought of things. But do we have a third proposal? I see. So there's the answer here was maybe there's a lot of fine detail in W0, and LoRa just because it makes these kind of broad, low-rank updates, it can encourage sort of massive shifts in behavior without destroying some of that fine-grained knowledge. So I like that. There's a classic approximation to matrices, which is you take a low rank and then you add a little bit of high frequency detail to the matrix. So sparse plus low rank is what this is approximate. There's a nice analogy there. So anyway, yeah, these are the interesting things. We're in this world where we have to think through things like that. And I see there's some other hands, but I want to move on. There will be other pop quizzes to answer. Yeah. Oh, it's okay.
It's related to this. So, do you think it's fair to expect LoRa's to handle big domain shift? Like, for example, you tune a language model for code generation with LoRa, because the capacity you give it is limited. So, is it fair to expect it to adapt to a huge domain shift?
That's a great question. Do we expect LoRa to be able to sort of be used for everything, even like massive domain shifts, like if we want to go from language modeling to code generation? I think it does get more complicated if you're really sort of shifting things. And the other thing, though, is as you have more data, you probably can get away with updating more and more parameters. I mean, one thing, though, to keep in mind about LoRa is as you increase R, once R becomes D, there's no difference between its flexibility and the full fine-tuning update. So it really is a continuum between something very different and fine-tuning the full model. So that's something to keep in mind. All right, let's go on. Well, actually, this is the moment for questions about supervised fine-tuning. So. All right, we're excited to get on to reinforcement learning. All right, so supervised fine-tuning is great, as we've said. Oh, yes, you had a question about.
Sorry, one question. Maybe you mentioned this, but maybe I missed it, but was LoRa applied to the feed-forward network parts?
It doesn't. You can do that, but in practice, people just fine-tune these kind of attention matrices. I actually don't know the sort of ins and outs of kind of what the state of the art with LoRa is these days. I mean, people, I'm sure, explore all of this stuff. But, one thing is the number of parameters in the feed-forward layers these days is massive. People are going with really, really wide ones. Also, things like, the mixture of expert stuff is making stuff very complicated in the feed-forward layers. LoRa, by just working with attention, it sort of neatly sidesteps a lot of those issues. But yeah, it's definitely an interesting question. All right. Okay. So we love supervised fine-tuning. We have techniques for doing it parameter efficiently. We have techniques for, keeping it from going off the rails with deviation penalties. But, maybe it's still not everything. So here are a couple of arguments for kind of why we might be concerned. So first, in general, in a generation problem where language is the output, language is incredibly expressive and multifaceted, and there are many possible correct answers to any prompt. But crucially for us, some of these will be easier for the model to generate, in some sense closer to the base model than others. So it would be nice, probably, if we could preferentially learn from those easy answers. So it's a bit like, when you start working on a new problem, you're probably going to approach it using the tools you had from the last problem you were working on, rather than sort of reinventing everything and starting from scratch. And you might think that we would like to encourage the model to have to learn less new stuff. So that seems desirable. Supervised fine-tuning, we just say, no, here for this input, give me this output. Another sort of argument that's sometimes made, I don't know quite what I think about this yet. I've gone back and forth on this. But supervised fine-tuning presents the learner only with positive examples. So you don't have the opportunity to learn from those, let's say, close examples that are actually very bad. So, sometimes, you're solving a math problem and you get it off by a sign. That's actually a really critical opportunity in math class to learn, it looks almost right, but you made a sign error somewhere. And, sort of in language model space, that is a really, really subtle difference. And so giving the model the opportunity to benefit from kind of negative feedback on sort of close enough examples seems intuitively like a powerful opportunity. And third, and I think this is really the most critical argument, is that some answers may just simply lie beyond the capabilities of the model. So let's imagine a pre-trained language model that's never seen any language but English. And now let's fine-tune it to generate translations from Serbian. Probably what this model is going to learn is that whenever it sees any Serbian, it will just start hallucinating English text. And the supervised fine-tuning data is lovely, but if you have 100 examples of Serbian paired with English, you're not going to actually be able to learn all of Serbian English translation. It's just simply not present in the language as a latent capability because it never had experienced that before. Now there's probably, if you had enough Serbian, supervised fine-tuning would work, but on the basis of a handful of few examples, it's probably not good. So really what we want our model to do, sometimes we want the right answer is to say, I don't know. And the I don't know, the truth of the predicate, I don't know, doesn't depend on something in the world. It depends on something in the model. And we don't know what's in the model. And so we'd like an algorithm, a learning process that lets us discover in some sense what's present in the model and not force it to do things it can't do. All right, so we're going to use reinforcement learning, specifically policy gradient learning, to address these problems. So our policy gradient algorithm, I heard you implemented reinforce yesterday. We're just going to use basically reinforce and all friends. And so what I've written here is the regularized form of this. So I've introduced this beta penalty here on the KL term. That'll be the tunable hyperparameter. And what we're going to do, it's a lot of, squiggles, but it's just basically saying we're going to have a collection of unlabeled prompts. So these are things like, what does 2 + 2 equal? And then we are going to sample randomly from that. Then we are going to sample from, we're going to take the expectation under the current policy, that's our p theta, conditional on that. We're going to sample a continuation. And then we're going to assume that we have a reward model that scores a continuation given a prompt. That's what I've written here, r, y of x. And that's our training objective. We're going to differentiate this with respect to theta. Use the and then that'll be our learning gradient. And in practice, of course, there are lots of tricks because we have to approximate that expectation. We have to control those gradients in various ways. We'll talk a bit about those toward the end of the lecture. So basically, we're assuming two new things. First, a collection of unlabeled prompts. So where do we get those? Well, it's actually, it's kind of a hard thing. It depends, if you have a task that you care about, presumably you might have examples of people asking for the task. You might have to pay someone to create them. You might be able to synthesize them. You might be able to, there are sort of general task collections out there that you can download if you want to sort of research this problem in theory. But it's actually a bit of a challenge. I mean, you can, if you're trying to build a generalist agent, you might actually think people can sort of ask anything. So I wouldn't say it's a trivial problem at all. And I think it doesn't get quite enough attention. You can also think about potentially generating them. You could maybe supervise, fine-tune a language model to do that. But we'll leave that for now and just assume that we have this nice collection of unlabeled prompts X. And now we need a reward model that's going to score the continuation of X of a prompt Y. So basically, this reward model is trying to answer the question of how a human would accept X as a continuation of Y, and do that by giving you a scalar real-valued number. So if I said, what is 2 + 2, and then my answer is 4, what's a scalar value for that? I don't know, is that infinity? Is it 1? Is it 10? It's a really hard problem. So we're going to have to use a bit of finesse to train this reward model. So let's talk about that. Oh, first, so just since I presume you saw this in Doina's talk, here's a standard sort of RL setup. We've got an environment. It's delivering rewards and states to an agent, and then the agent's giving it actions, and we do this environment. The RLHF setup is a little bit different in that prompts are giving us, you might say, states, and then the reward model and agent are basically taking it from there, where we're continuing to take actions. The environment is so simple; it's just add to the end of the state that becomes your sequence, and then the reward model just gives you a reward. And in practice, I will say we're going to be assuming our reward model only gives you a signal about goodness at the end of the kind of once the whole language thing has been generated. It would be much nicer, obviously, if we got sort of feedback for every word. It would simplify learning. Credit assignment would be easier. In practice, we don't have such reward models. That's a very hard problem. Okay, so as I said, this is what we want. I'm sorry, there's a slight shift in notation reflecting the fact that I made these slides in a different order. So here's our problem. We want this model, R with some parameters, phi, to take a prompt and a sample and deliver a real valued number. So what are the pieces to building R? So we need some kind of data that gives an indication of the goodness of some sampled responses. And so what kind of data are we going to use? We're going to use pairwise preference data, where we're going to have pairs of alternative continuations to a prompt, and then we're going to have human judgments as to which is better. So that's going to give you, so rather than asking you to give me a scalar, how good is it to answer 4 to 2 plus 2? Is it 10? Is it 1? Is it 1,000? You just have to say, well, I like the answer 4 better than I like the answer 5. So that's a little more objective. And now we need a model that learns a scalar reward quantity from preference data. And the way we're going to link pairwise preference data to scalars is via a classic model called the Bradley-Terry model. And then think about how hard the reward modeling problem is. It's as hard as probably everything else. So we want it to really understand language. So we're going to supervise fine-tune an LLM to make it into a reward model. So all the stuff we learned at the beginning of this, we're going to bring back now. All right, so pairwise preference data, as I said, it's easier to elicit than a global goodness score. We can generalize it easily to ranking. So if we take, rather than 2 samples or 2 continuations from each prompt, we can get 10, and we can sort of have someone rank them. There are generalizations of this model that can do the same sort of thing. And so the Bradley-Terry model is really simple. It just says that given a pair of items A and B, the Bradley-Terry model gives a probability that A is preferred to B in terms of a positive score associated with each item, which just looks like this. So the probability is the score of A divided by A plus B. And we're assuming that these scores are, as I said, greater than or equal to 0. And since we want a real valued scalar, R, without that positivity constraint, we're just going to exp our R in our sort of Bradley-Terry instantiation and do this. And those of you who, like a little bit of algebra might notice that this is just the logistic sigmoid function of the difference in the reward model applied to item A and the reward model applied to item B. So with this handy log linear model form, so P of A greater than B equals sigmoid of the difference of these 2 reward values, we can easily define a loss function, binary cross entropy, very, very simple. We've got a bunch of data exactly in the form of these binary decisions, and now we can train our model. Okay, so another pop quiz. So first, what do I mean by log linear model here? These are old-fashioned terms. I was just wondering if people still knew that. It just means that the response of the model is linear in the log of the log. So if we take the log of this, then we just have this like linear difference R between the R's in the prediction we're making. So that also means we can optimize this thing. You know, if R was a very simple kind of linear model that we could optimize directly, we could find a global solution. But here's a more interesting conceptual question. Okay, so for each pair, let's assume we have labels no preference, weak preference, and strong preference. So 2 questions. What would the benefit be of this labeling scheme, and how would you alter the reward model? And I'm going to confine this to 3 minutes so that we get through things in time for the next speaker. So does anyone want to take a crack at either of those?
For mathematics, where these are exact strong preferences are better because there is an exact answer. For language-based questions, then weak preferences may be correct.
Okay, so he was pointing out that in some domains there are like absolutely correct answers, like mathematics, and others you might have sort of degrees of preference, some, you know, stylistic things in language, for instance. So I would say one way of saying that is we have a task that becomes more natural to annotators. And people have to, you know, this is human feedback. We have real humans. You know, those of you in this room are on the sort of, let's assume we've got the data side, but there are people out there who are creating this data, and we want the task to be easier for them. So that's definitely useful. Yeah.
It might reduce the noise on the report. For instance, if you in a continuous scale, then for some annotators it's 4, to some annotators it's 5. Then you might actually have a noise in the order if you use a continuous function. But with the binning, I think you might mitigate that.
Yes, so this answer was that we might mitigate the noise. So if you sort of treat all kind of big updates, because there is a preference disagreement as equally important, you might kind of overfit on some marginal cases. So there's a learnability or stability kind of argument there. Yes? This was the proposal that there might be more signal because it's sharper data. I think that's a variant of this learnability thing. We have just less noisy data. It's in some sense you can imagine the standard labeling as flattening this out and just obscuring important differences. Very much so. Yes.
Maybe it could be also a cost thing because if we see no preference, then we can just pass on that and not do anything.
That's an interesting question. So if there's no preference, maybe we pass on it. I actually think we don't want to pass on it. I think we want to make sure that we give the same score to both scores. If the reward model is saying, you know, this one is great and this one is bad, and we've given it a score of no preference, I think we actually want to sort of change the learning. So unfortunately, we do need to go along, but I want you to think about how you might solve this. There are a variety of ways to implement this, and just think about what you come up with. It's a fun problem. All right, so let's talk about now fine-tuning our language model to be a reward model. And I'm going to go into some standard architectures for this just because these are important. And I just want to reiterate here that I find it like these are common, but the idea that we can't trust our reward models too much. This is a hard problem. In some sense, I think it's almost harder than the language modeling problem itself. Because, look, if we've got a language model that does what it's supposed to, even if it doesn't do it in all possible ways, we're happy with the language model. However, in reward modeling, we need to be susceptible to distribution shift. We're going to be using this in a reinforcement learning loop. The model will be behaving differently as training progresses. We need that reward model to be giving reliable reward signals at every step, and it's not always going to. So this is a hard problem. So, and this is why it's important that we fine-tune a language model to be a good reward model. We can't start from scratch. There's too much to learn. So we have two options, of course, fine-tune an autoregressive language model or fine-tune a decoder-only classification model, for instance, BERT. We're going to talk about the autoregressive one here, but both are fine. So let's start, oh yes.
Different sentences, different sentences.
Uh,
Afterwards, when you have two sentences, you send it to the QMAC. The QMAC is back the feedback, but in the model, if you update the weights, it's not going to be the same model to use to generate those two sentences.
Yes. Yeah, okay, so the question was, how do we get the samples that we ask humans to do? And if we update the model that we're sampling from, how do we, it's not going to be the same. So in practice, people use all kinds of different techniques for getting these pools of samples. Sometimes they sample from one model with different random seeds or different temperatures or different slightly different sampling algorithms. We, don't in practice, although these language models admit sort of perfect sampling where we get samples actually proportional to the language model's probability, we actually tend to sample from a biased version of the language model because it tends to be sort of nicer for reasons that we kind of think we understand, but not completely. And so because we're trying to train a reward model and not directly using the human feedback in the reinforcement learning step, we just try and get a big diversity of samples. So we often go to different models, especially if you're putting together a public data set, or you're trying to build a reward model that's going to be useful over many generations of model. So we try and we do a variety of things to get artificial diversity. But this is a hard problem. Like figuring out what that sampling discipline is for labeling is huge because annotation is expensive for anyone. It takes time. It probably takes money. It's like. And yeah, I don't think we have a great sort of principled answer for this. People are definitely looking at things like active learning and stuff like that to kind of do this. But in practice, we identify sort of deficiencies in the reward model and then try and do sort of targeted sampling in those regions. But it's kind of like the battle between spammers and spam detectors, where it's a constantly, there's a bit of an adversarial relationship between what the model wants to do and what the reward model wants to sort of adjudicate. Okay, so let's talk about fine-tuning a language model to a reinforcement learning model. So here's a picture of a sort of autoregressive transformer for sort of generating the first 5 words. I realize now I have an off by 1 error in my inputs. My apologies for you sharp-eyed ones, or more sharp-eyed than when I was making these slides yesterday. And the first thing we're going to do is say, well, we don't want to make these predictions at the top. We aren't actually interested in generation. So often what we do is we just take the output of the transformer, so these top layers, and we just pool the activations, the hidden layer that are there. And we just do this by taking the average. Project that through a linear layer or maybe an MLP, depending on the amount of data you've got, and then project that out onto a single scalar. That gives us a score. And then obviously we have to learn the parameters of this linear layer. Maybe we backpropagate further. Maybe we add some LoRa components inside. All the options for fine-tuning are available. Plus we've got these few extra parameters. So one sort of critical practical thing is, because we're going to be training and we need to know, remember our loss function depends on the difference of a positive and a negative component. We need to basically put the pairs into the batch. So we're always going to have even number size batches, and they're going to have, just for each prompt, the positive and negative guys next to each other, and that'll let us then sort of collapse those batches into half the size and compute that loss function in a nicely batched way. So a couple things. So one thing people often do is they kind of chop the top layers off the transformer when they're adapting it in this way. The rationale is that when you're getting near to the top, you're often sort of getting very sharp about making a prediction about exactly what's coming. And in the lower layers of the transformer, you're kind of representing things at a more conceptual level, which might be a representation that's better for making decisions about like goodness of continuations and sort of more global properties. Again, it's all a bit of a black art. You know, different pre-trained models maybe behave a little bit differently here, but it's one thing to do. So an alternative is we can think about, well, you know, what is pooling but a kind of attention, right? That's just sort of saying we're attending evenly to all of the positions in the input. Well, we have a mechanism for attending, and we have this great technique, the query, which allows us to say exactly what are the things we want to be attending to. Maybe there's certain little bits that are presented on those values elsewhere in the model, and we can introduce a new query matrix, and that will be used to drive sort of one last attention layer, which just sees everything else, and then we project that out onto a single scalar, and we're done. So these are a couple of things. So I'm going to skip this pop quiz. We can talk about it afterwards, because I want to talk about the limits of this and finish up with the RL algorithms. So as with supervised fine-tuning, RLHF doesn't do it all. So an initial pre-trained language model may be very far from our desired behavior. As you saw that, it would be hard to know how to sample long enough to start moving that policy that we had at the start that was talking about the Treaty of Versailles when I asked about, you know, supervised fine-tuning into sort of a reasonable part of the space. So in practice, supervised fine-tuning followed by RLHF is extremely effective. Second, really critical thing is reward models are gameable. There's no perfect reward model. And what this means is there's often an output that a human dislikes. So one common example we see is you just start repeating content, you know, kind of over and over again. Turns out that reward models often just really like this. It's very unnatural. It seems like it would be easy to detect for the model, but sometimes they just, you know, they just give a high score to this. Deviation penalties can help here, but basically you got to keep an eye on things. You can't just because you're getting a good held out reward signal or reward score doesn't mean that you haven't sort of started, you know, gotten into this conspiracy of, you know, the reward model just say, I'm going to give, if you just repeat a bunch of content, I'm going to give you a good score, and the learner says, okay, I'll do that, and you don't want that. And finally, reward models are expensive. These are, you know, it's another massive model in terms of data, training costs, execution costs. And in some cases, supervised fine-tuning data may just be plentiful and cheap. For instance, translation, a problem I used to work on. There are translations everywhere in the world because translation is an important human activity. And so that data exists, even though it wasn't created to be data, we can transform it into fine-tuning data. That is something to be used, and you know, in the RLHF setup, it doesn't really have a role to play. Okay, we'll skip this. It's just RLHF in one slide. The slides will be available. You can go back and refer to this. I'll end by just saying a couple of words briefly about this policy gradient objective. So the big problem here is we have this intractable expectation. And because this is a critical technique, but approximation is like open-ended, how to better approximate the expected reward is just the subject of much work. Basically, you know, some of the big strategies are variance reduction strategies, strategies for taking conservative updates. The idea is you don't ever trust a gradient, so you don't want to take a massive leap on the, you know, sort of advice of a single gradient. And strategies for reducing the variance of the gradient rather than just of the expected reward. And the current default here that sort of everyone uses and no one really loves is probably the PPO algorithms, proximal policy updates, which kind of combine all of this stuff. There's a parallel interesting line of work that I just wanted to bring up here at the end briefly, which is to attempt to dispense with reward models while still being able to benefit from human preference data. And this is a really clever idea that's being explored in a variety of places. And the notion here is that the log probability of a language model is itself a kind of reward. And there's a very deep sense in which that is the case. if you think about kind of the limiting distribution that you get when you optimize that policy gradient thing. And this hidden reward model can therefore be aligned to human preferences using the same Bradley-Terry trick that we use to train our reward models. And this has the side effect of aligning the generations. And this gives what's called the direct preference optimization family of algorithms, DPO. These are kind of the subject of investigation. Does it work right now? Well, it's super convenient, no more reward models, but it does seem to perform less well under most circumstances. You obviously sacrifice a bunch of the benefits of RL, like exploration, so that's sort of the intuitive sense there. So anyway, stop here. I think we're basically at time, but maybe we can take a couple questions. Okay. Sorry, I think, why don't we start, someone behind you who we haven't heard from first. Yes.
As far as I understand, like human food is very expensive, like exclusively plant-food, and it's very expensive. Are there like approaches which use like large models feedback, like they include these models, but something like that?
Yeah, so I had a slide of the topics we didn't get to, and I took it out this morning, and the question was, so human feedback's expensive, but we have these large models that can sort of mimic humans. Can we use them to give the feedback? And indeed, this is a very, very interesting area of research. It can be quite effective. It's sometimes called RL with AI feedback. And you prompt these models to critique or otherwise, make decisions about that, perhaps with a list of kind of statements of norms. Then it's sometimes called constitutional AI, where there's a constitution of kinds of behaviors that you want. That's often in a safety context, and this can be extremely effective. And I think. In general, feedback is one of these things where we're going to see a lot of joint human model sorts of developments in the coming years, where we want to sort of deploy people not to do every single ranking task, but to do the ones that are going to be that are extremely sensitive and need care. And I imagine in a few years, probably this will be something we can replace with models entirely. Yep. Yes.
I have a question. Recently there was a model called Golden Gate Bridge Law, and it's found a way to relate any question of Golden Gate Bridge how they achieve that behavior.
Oh gosh, there was recently a model called Golden Gate Bridge Club, and any question you asked it would find a relationship to the Golden Gate Bridge. I did not see this. It does sound like the sort of thing that actually language models are very good at. If I were to guess, it would probably be this like combination of a recipe of some stuff with supervised fine-tuning, where they had a few examples of, kind of off-topic pivots to the Golden Gate Bridge, plus it's pretty easy to imagine a reward model that has like two components. One that is a sort of standard reward model, and then another that just sort of makes sure it's talking about the Golden Gate Bridge and adds those together. You do some supervised fine-tuning, and suddenly you've got a model that kind of does what it says, but also talks about the Golden Gate Bridge all the time. That's my guess. One last question. All right.
What happens when the pairwise preferences are not transitive? For example, is data quality problem?
Oh, that's a great question. So what happens if pairwise preferences aren't transitive? And in fact, if you elicit preferences from people, guess what? They're not transitive. This is a huge problem. I mean, the model you can show, it leads to these basically, cross entropy just ends up with this kind of minimum. You can see what the stable solution of the objective is, and you're going to be inconsistent with some set of them. And I think the hope is that in practice, sort of for critical things, there are no there are no intransitivities, and then sort of in more, ambiguous areas, that's where that sort of uncertainty lives. But I think I'm more concerned with this. I ask our pairwise preference people this all the time, and they sort of try and leave the room quickly. So. All right, well, it's been great talking to you all. Enjoy the rest of your EEML.